What if I told you that the number of directions you can move in is not random?
What if one extra direction would break the sky?
Or one less would erase everything interesting? Today we're digging into a weird question with huge consequences.
Why does space have 3 dimensions?
Not 2, not 4, not 7.
If you have ever stared at the night sky and wondered why it works at all, stay with me.
We're going to use gravity, atoms, quantum fields, and chaos to see why 3 keeps showing up.
Imagine you are floating in space. No walls, no grid, no labels.
You can still point in directions.
Left and right are 1. Forward and backward are different.
Up and down is the 3rd.
That feels obvious because you grew up inside it, but obvious is not an explanation.
The real question is why the universe picked this setup.
One common answer is that physics demands it, but that sounds like a dodge.
Physics is a description of what happens here.
So why should the description require the stage to be 3-dimensional? The better version of the answer is this.
Many of the structures we rely on only work if space has 3 dimensions.
Change the number, and the same rules create disasters. That does not prove 3 is necessary in some ultimate sense.
But it does show that 3 is incredibly special.
Let's begin with gravity and planets. This is the part where people warn you about math.
So here's the deal.
There will be exponents, but it will not hurt unless you are allergic to exponents.
In that case, I recommend watching someone contour their cheekbones while whispering soothingly about prime numbers.
In our universe, Newton's law of gravity predicts that the force of gravity weakens with distance. Specifically, it drops like 1 over the distance squared.
Say the distance from the sun to a planet doubles.
The force becomes 4 times weaker. Y squared?
There is a clean geometric reason.
The influence of a point source spreads out. In 3 dimensions, the spreading happens over the surface of a sphere.
A sphere's surface area grows like the radius squared. Same total amount of field, bigger sphere, lower density.
So the field strength falls off like 1r squared. Now, imagine space has a different number of dimensions.
The surface around a point is not a normal sphere anymore.
It is a higher dimensional sphere, and its surface area scales differently.
In a space with d dimensions, that surface scales the radius to the d minus 1.
That means the field strength scales like 1/r circumflex, d1. So, in 4 dimensions, gravity would fall off like 1r cubed.
In 2 dimensions, it would fall like 1 over r to the first power. Same idea, different dilution.
So far, this is a small change. Just adjust the exponent and move on.
But planetary motion is a delicate balance.
A planet does not just fall inward, it also has sideways motion.
That sideways motion behaves like a resistance to falling.
In the simplest picture, you can wrap that sideways effect into an effective outward term that drops like 1/r circumflex 3. The key point is that this outward contribution comes from angular momentum.
And the orbit is always confined to a plane, even in higher dimensional space.
So that part keeps the same radius dependence. Now you set the inward gravity term equal to the outward effective term.
That gives you a possible orbit radius.
But possible is not the same as stable. Stability is the real test. A stable orbit means this.
If you push the planet slightly outward, it should drift back.
If you nudge it slightly inward, it should recover. An unstable orbit means the opposite.
A small nudge turns into a runaway.
Either the planet spirals inward and crashes, or it escapes forever. To check stability, you look at how the total effective force changes with radius.
In plain language, you ask which side wins when you move slightly off the balance point.
If the restoring tendency points back toward the balance, you are good. If it points away, you are doomed.
When you do that calculation, something striking pops out.
The stability condition boils down to a simple inequality. The dimension d must be less than 4.
In other words, for ordinary inverse power gravity that comes from Gauss-style spreading, stable closed orbits stop working once you hit 4 spatial dimensions.
That is a wild result. It means if you keep everything the same, but space has 4 dimensions, solar systems become fragile. Planets do not settle into long-lived, gentle ellipses. The slightest disturbance sends them inward.
In that world, many planets would crash into their stars.
And if you try to form complex, layered systems over billions of years, you have a problem. This argument is often linked to early work by Paul Ehrenfest, who explored how stability constraints can single out 3 dimensions. The spirit is simple. If you demand long-term stable structures under familiar force laws, you do not have a free choice of dimension.
3 starts to look privileged.
But notice something important. This does not automatically kill 2 dimensions. In 2 dimensions, the gravity law would look different. The force would fall like 1r.
That can still produce stable orbits in the sense of the effective potential.
So the solar system stability argument says 4 and up looks bad. But it does not say only 3 is possible. 2 can sneak through. And there is a fun connection here. In some modified gravity ideas, such as modified Newtonian dynamics, the deep regime can behave more like a 1r force in certain contexts. The motivations are totally different, and this is not the same as living in a flat 2-dimensional space,
but it gives you intuition.
Change the fall-off, change the orbit behavior. Exponents matter. Okay, so planets can still work in 2 dimensions. Would that save a 2-dimensional universe?
Not so fast.
Planets are made of atoms. Chemistry matters more than orbits, and atoms bring their own stability trap. Let's talk about the hydrogen atom.
Do not worry, we are not going to pretend electrons are tiny planets.
That picture is misleading. Electrons are quantum objects. They do not travel on neat little tracks, but the stability question remains.
Why does the electron not collapse into the nucleus?
In 3 dimensions, the electric attraction between a proton and an electron follows the same inverse square pattern. Again, it is a field spreading over a spherical surface, so the potential energy looks like 1r. As the radius shrinks, the potential gets more negative.
That sounds like the electron should fall inward forever.
The reason it does not is quantum uncertainty. If you try to trap the electron in a smaller region, its momentum uncertainty grows, and higher momentum means higher kinetic energy, so squeezing costs energy.
The electron balances these competing effects.
Attraction wants a small radius. Uncertainty pressure wants a larger radius. The minimum of the total energy defines an atomic scale. You can estimate this with a simple uncertainty argument.
Suppose the electron is localized within a region of size r.
Then its momentum uncertainty is roughly h bar r. Kinetic energy scales like momentum squared over twice the mass. So that goes like 1 over r squared. Meanwhile, the Coulomb potential energy goes like -1 over r.
Add them.
At large r, the potential dominates and the energy is near 0. At very small r, the kinetic term explodes positively. So there is a sweet spot where total energy is minimized. That is the rough story behind atomic stability.
Now change the number of spatial dimensions again.
The electric field spreads differently. That changes the force law and therefore the potential. In d dimensions, the force scales like 1 over radius to the d minus 1. The potential then scales like 1/r circumflex d2 for d2.
2 dimensions are special because the potential becomes logarithmic rather than a simple power law.
Here is the punchline. When d increases, the attractive potential becomes more singular at short distances. It drops faster as you approach the nucleus. But the uncertainty-driven kinetic pressure still scales like 1r squared in the basic estimate. The competition shifts.
In 3 dimensions, the balance is healthy.
In 4 dimensions, the attraction becomes too strong near the origin. The minimum can disappear or move toward collapse, depending on the details of how you generalize the laws. And in many treatments, higher dimensions destroy the familiar, stable, bound state structure. The electron is pulled inward too aggressively.
The shelves you rely on for chemistry stop behaving the way they do here.
Again, 2 dimensions are weirdly borderline. The logarithmic potential changes the story. Some bound states can exist, but other pieces of physics start to behave strangely. Even if you can arrange a stable atom, the rest of the world is not guaranteed to cooperate. So, with planets and atoms, we have a pattern. 3 dimensions support a wide range of stable, long-lived structures.
4 or more tend to create collapse problems for inverse power forces.
2 might survive, but it comes with oddities. Now we reach a deeper reason, and this one is less about pictures and more about consistency. It involves quantum field theory, the tool we use to describe particles and forces at a fundamental level. Here is the weird thing about quantum field theory. A particle is not just a little bead moving along a line. In the quantum view, every path contributes.
Every interaction that is allowed can occur as a fleeting virtual process.
An electron can emit a photon and later absorb it. That photon can briefly fluctuate into particle pairs and recombine. and then the electron keeps going, carrying the scars of those possibilities. When we calculate a measurable quantity, such as how an electron moves or scatters, we sum over contributions from all possible internal processes. In practice, this means we evaluate integrals over momenta and energies across a vast range, including extremely high momenta, and that is where trouble shows up. Many of these integrals diverge.
They blow up to infinity.
At first, infinity sounds like failure, but physics found a workaround. In many theories, the infinities have a structured form. You can absorb them into a finite set of parameters. You redefine the mass, the charge, and a few other constants in a controlled way. You then fix those constants by measurement.
After that, the theory makes real predictions.
That process is called renormalization. The basic idea is not that infinities are fine. The idea is that the bare parameters you call are not directly measurable. Only the renormalized combinations are. If the infinities can be contained with a finite number of redefinitions, you still have a predictive theory. But here is the catch. Whether this works depends strongly on the number of space-time dimensions.
Dimensionality controls how badly integrals diverge at high momentum.
It also controls the mass dimensions of couplings, which tells you whether interactions grow or shrink at short distances. In 4 space-time dimensions, which is 3 dimensions of space plus 1 of time, the standard model is built out of interactions that are renormalizable by power counting. Gauge couplings and the Higgs quartic coupling can be dimensionless in that setting. That matters. Dimensionless couplings are the sweet spot for renormalizability. You can organize divergences, absorb them into a finite set of counterterms, and move on.
Change the number of dimensions, and the bookkeeping changes.
A dimensionless coupling may acquire dimensions. If the coupling has a negative mass dimension, the interaction becomes non-renormalizable in the traditional sense. You do not just get one kind of divergence. You get an endless tower of divergences that demand an endless list of counterterms. Each one comes with a new parameter that must be measured. If you need infinitely many measurements to define your theory, the prediction collapses.
The theory stops being a sharp machine and becomes a loose catalogue.
This is why the dimension of spacetime is so central to quantum field theory. The renormalizability of the interactions depends on it. So when you ask, could the standard model work in a different number of dimensions? The common answer is, not in the same way. You can build quantum field theories in other dimensions, yes, but the specific structure of the standard model, as the renormalizable gauge theory we know, is tuned to 4 spacetime dimensions. There is a nuance here. People sometimes say, in other dimensions, you get infinitely many infinities. That is too dramatic as a blanket statement.
There are renormalizable theories in other dimensions, including super renormalizable ones in lower dimensions.
And there are non-perturbative tricks in special cases. But the core idea remains. The balance that makes our familiar particle physics predictive is tightly connected to dimensionality. The set of interactions that behave nicely changes when the dimension changes. So this becomes a powerful argument for why 3 spatial dimensions are special. It is not just that planets might fall in.
It is that the entire framework we use for fundamental forces,
with the observed particle content and interaction types, is deeply linked to living in
3 spatial dimensions.
Gravity, the force that shapes the cosmos, is the odd one out. If you try to quantize general relativity in the same perturbative way, you run into non-renormalizability in 4 spacetime dimensions. The Newton constant has a negative mass dimension in 4 dimensions. That is a classic warning sign. It tells you the theory needs an infinite set of higher order terms as you push to higher energies. Does that mean gravity cannot be quantum? No.
It means the naive approach fails.
Many physicists treat general relativity as an effective field theory at low energies. Others explore new structures, such as asymptotic safety and string theory. The point here is not to solve quantum gravity in a sentence. The point is that renormalization arguments are sensitive to dimension, and gravity's behavior highlights that sensitivity. So we now have 3 big threads. First, long-lived solar systems are hard to maintain in higher dimensions under simple force laws. Second, stable atoms and chemistry face similar pressure when you change dimension. Third, the internal consistency and predictive power of our best quantum theory of particles and forces depends strongly on the dimensional setting. And the standard model's nice behavior is tied to 4 space-time dimensions.
But there is one more ingredient that often gets ignored.
And it is my favorite because it sounds almost philosophical while still being math. Complexity. Even if you had stable orbits and stable atoms, you still need rich dynamics. You need systems that can store information, evolve, adapt, and build structure. That often means nonlinear behavior. Sometimes it means chaos. Now, chaos is one of those words that people use loosely. In physics and math, chaos has a technical meaning. It involves sensitive dependence on initial conditions. Tiny differences grow over time until prediction becomes impossible in practice. The classic butterfly effect idea comes from this. Here is the surprise. Continuous time chaos requires a minimum dimensionality. In a continuous dynamical system, if your state space is only 2-dimensional, you cannot get a strange attractor. You can get fixed points, you can get limit cycles, you can get some kinds of complex-looking motion, but genuinely strange attractor chaos is ruled out under broad conditions.
This is linked to the Poincaré-Bendixson theorem, which restricts the possible long-term behavior of 2-dimensional Koth long-term.
So, in a 2-dimensional space, many systems would have less room for chaotic richness, at least in the continuous time sense. You could still have complex behavior in discrete systems. You could have chaos in maps. The logistic map is a famous example, and it can be chaotic with a single variable updated step by step. But if your fundamental physics is smooth time evolution, then 2-dimensional state spaces are too cramped for the kind of chaos we associate with rich natural complexity. 3 changes everything. The moment you move to 3-dimensional flows, chaotic attractors become possible. The Lorentz system is the poster child.
It is a set of 3 coupled differential equations that began as a simplified model of atmospheric convection.
And it produced this butterfly-shaped attractor that never repeats and never settles, yet stays bounded. That was a shock. It showed that deterministic equations can generate unpredictable long-term behavior purely because of the geometry of the flow in a 3-dimensional state space. So 3 dimensions open the door to chaos in continuous time systems. And chaos, when balanced, can be a source of complexity. It can help create diversity of outcomes. It can amplify small differences into meaningful variety. But it is also dangerous.
Too much chaos can destroy structure.
So the story becomes a balancing act. Now imagine increasing the number of dimensions again. In high-dimensional systems, chaos becomes easier to produce. There are more directions for instabilities to grow. There are more ways trajectories can twist and fold. That does not mean higher dimensions equal impossible. It means the world may become more turbulent in a deep way. The challenge is to get complexity that is rich but not overwhelming. You want dynamics at the edge, not dynamics that instantly shred any stable pattern.
So in this 4th thread, 3 dimensions again looks like a sweet spot.
2 is too orderly in continuous time. 4 and above may be too unstable. 3 is where chaos can exist, but it is not automatic everywhere. It can be localized. It can coexist with stable islands. It can be tuned. That is exactly the kind of environment where complexity can bloom without being instantly erased. At this point, you might be thinking, okay, so 3 dimensions seem lucky. And yes, that is the feeling.
But notice what we've really done.
We have not proven that a 2-dimensional or 7-dimensional universe is logically impossible. We have shown something more practical and more grounded. Many key ingredients of the world we see rely on 3 dimensions working together with our force laws and our quantum framework. Remove a dimension and you reduce the degrees of freedom. Forces look different. Potentials look different. Field theories behave differently. The kinds of long-term motion you can get change.
Add dimensions and you change how influence is spread, how bound states work, and how divergences behave.
It is not just one thing that breaks. Multiple independent pillars start wobbling. There is also a subtle point people miss. When physicists say, in d dimensions the force law becomes 1 over r to the d minus 1, they are not just making it up. That is tied to how flux spreads with geometry. It assumes the same kind of conservation and locality you are used to. If you change more than one assumption, you might get different results. You could imagine bizarre worlds with different laws that still allow stable structures.
But then you are not just changing dimensions.
You are changing the whole rulebook. So if your question is, Why do we live in 3 dimensions with these laws? Then these stability and consistency arguments become compelling. They tell you 3 dimensions are not arbitrary. It is a configuration where many constraints align. But if your question is, why does the universe exist with these laws at all? Then we are drifting into deeper territory. The honest answer is that we do not know. We can map the consequences. We can identify the specialness.
We can show that 3 dimensions support stable atoms, stable solar systems, predictive quantum field theory, and the right kind of chaotic complexity.
But why the universe selected this option is still an open mystery. And maybe that is the right place to land, not with a smug physics wouldn't work, but with a more interesting thought. Physics works the way it does because it evolved in a 3-dimensional arena. 3 dimensions are not just the stage, it could be part of the script. So the next time you walk across a room, notice what is hidden in that simple act. You can move left and right.
You can move forward and back.
You can move up and down. That third option is not just convenience. It might be the thin line between a universe with atoms, stars, chemistry, weather, life, and memory, and a universe that either freezes into simplicity or collapses into instability.